Hey, welcome back everybody. In this section we're going to work with the properties of Boolean algebra to simplify networks. That is to say we're going to do some algebra, but it's going to be Boolean algebra instead of traditional algebra. So let's start by reviewing the properties of Boolean algebra that you learned in the previous lesson. Okay, so in our last lesson we established these properties of Boolean algebra, some of which are the same as traditional algebra, some are not. The commutative property says that either operation, addition or multiplication, can be reversed. A plus B is the same as B plus A, and A times B is the same as B times A. That's the same as traditional algebra. The associative property says that you can group switches together in any way you want over the same operation. B plus C is the same as A plus B plus C, and the same thing is true for multiplication. The identity property says that A plus 0 is A and that A times 1 is A. That's true for traditional algebra. And of course we have double negation, that if you reverse the state of a switch twice, it ends up back where it started. The 0 and 1 properties, A times 0 is 0. And then we come across our first one that's not the same as traditional algebra. A plus 1 is 1. That's because A or 1 will always be 1. That is, the choice between a switch or a continuous circuit will always have a continuous circuit. The complement property says that if we always have to choose between a switch and its negation, one of them will always be on, and so A plus the negation of A is 1. But if we put them in series, A and its switch in the opposite state, one will be open and one will be closed. That'll always leave a broken circuit. A times the negation of A is 0. The distributive property says A times B plus C is AB plus AC, but then we have a different form of distributive property. A plus B times C is A plus B times A plus C, and in my opinion that's one of the trickier properties to get a feel for. The idempotent property says that A or A plus A is just A, and A times A is still just A. And De Morgan's property says you can break the line and change the sign. So the negation of AB is the negation of A plus the negation of B separately. Or the negation of A plus B is the negation of A times the negation of B separately. Make sure that you're comfortable with these properties. We're going to be using these throughout our lesson. So let's use those properties to simplify some networks. What does it really mean to simplify? Well, a network of switches is simplified when it uses the lowest possible number of switches to represent an equivalent expression. So we never want a switch network to be more complex or to have more switches than necessary. Let's look at a simple example. Let's draw the network for A or AB, and then we'll simplify it using Boolean properties, and then look at the simplified network. So, step one, let's draw this network, A or A times B. So A or means that right off the bat we're going to have a parallel switch network here where A is one path and the other path is A times B, that is to say A and B in series. So there's our original network. Step two, we want to simplify this using Boolean algebra. Let's do that. We'll start with A or AB. Now, how can we simplify that? Well, think about A as being A times 1. That's the identity property, so we can rewrite that as A times 1 plus AB. But now you can see that we have a common factor of A here, and we can use the distributive property to undistribute that in a sense, or in traditional algebra we'd say that's like factoring it out. We'll factor the A out, and we're left with 1 plus B on the inside. And that should feel like normal algebra. You've probably done that before. Now, on the inside of parentheses, we have 1 or B. That is to say a circuit that's always closed, or B. And if you look at our original network, it means that we have to go through A no matter what. And then we can either go through the top branch, which has a continuous circuit, or the bottom branch, which has B. Well, we'd choose the continuous circuit every time. And so that means that 1 or B, which is one of the 0 and 1 properties, says that this is the same as A times 1. But of course that is the identity property, and we can see then that this Boolean expression really simplifies to A. And it should make sense then that in order to have a complete circuit, really what has to happen is A has to be closed. If A is closed, it doesn't matter what's going on in the bottom path, we'll have a complete circuit. And we can't get through the bottom path without A being closed anyway. So step 3, draw the simplified network. Well, that's real easy. A simpler way to represent the same result is to say we need switch A, and that's all. Notice here that our original expression had 3 switches in it. That is not simplified because we were able to write an equivalent expression using 1 switch. Let's do another one. Let's draw the network for A plus 1 times B times 0. We'll simplify and then look at the simplified network. So for starters, we have A or 1. Let's draw those two in parallel. And so we have A or 1. That's multiplied by B or 0. That is to say it's in series with another parallel path that is B or 0. There's our original network. Now let's simplify that using Boolean algebra. A or 1, that's our 0 and 1 property. A or 1 means that that simplifies to just 1. And B or 0, we can go through path B or not go through at all. Well, I guess that simplifies to be B. That's our identity property. And the other identity property that says that 1 times B is just B. And so this tells us that really the simpler way to have this switching network is to just have switch B. That's really all that matters. And that should make sense because given our first 2 parallel paths, we can go through switch A or go through a 1, which means that that switch is always closed anyway. So that means that A is irrelevant. And for the second parallel path, 0 is always open, so we can never get through there. We have to go through B. So in fact, the only real path here is to go through switch B, and our Boolean algebra shows that. We reduce this to 1 switch, and we're done. Okay, let's do another example here. We won't worry about the sketch of the network here. Let's just use Boolean algebra to simplify this expression. A times B plus C plus AB. Well, here we go. The distributive property says that we can distribute in that A, and so we get AB plus AC plus AB after the distributing. But the commutative property says we could switch these two around so that the two ABs are next to each other. It's not really a critical step, but we can do that. The idempotent property says that AB or AB really just means AB. Remember, you can have an apple and a banana, or you can have an apple and a banana. Well, that really means your only choice is to have an apple and a banana. Or you can have an apple and some cherries, right? And so the network simplifies to be AB or AC, but there's a common switch of A here. We don't need this in both. If you can have an apple and a banana, or an apple and some cherries, that means that really you're going to have an apple regardless. Your real choice is whether you want banana or cherries. And so we can have A times B or C because we factored out or used the distributive property for A. Now we've got that down to just 3 switches, and that is completely simplified. It means that this AB term up here was actually unnecessary, but we proved why. Okay, I'd like you to take a shot at this one. This is a practice problem. See if you can simplify ABC plus BC plus AB using the Boolean properties. Unpause to see if your solution matches the one I come up with. Okay, well, the way that I'm going to do this isn't the only way to simplify this, but we should all get the same result. So you might use a different set of simplification steps, but hopefully we end in the same place here. If you take a look at these first 2 terms, ABC or BC, they have a common factor of BC. Now, we'd like to factor that out, but we have to recognize that this is really ABC plus 1 times BC, which means the BC could be factored out, just like in regular algebra, and that leaves us with A from this term, or a 1 from our second term. But a or 1 simplifies to be just 1. And so we have BC times 1 plus AB. But BC times 1 is just BC or AB. And already we've simplified this quite a bit. But here again, we've got a common factor of B here, then that can be pulled out to the front. Right now we have 1, 2, 3, 4 switches. By factoring that B out, we're left with B times C plus A, which means we can get this down to 3 switches, and that is our simplified expression. If you got that, nice job. If you didn't, make sure that you understand the reasoning for getting that. This step right here is particularly tricky, recognizing that BC is common to both, and if you factor that out, it leaves a 1. That's just like traditional algebra, so if you've had some algebra, that'll probably feel less confusing than if you've not seen that in a while. Okay, I want to look at one more with you that I think is particularly tricky. A plus B times A plus C plus BC. Let's simplify that. Right now we have 1, 2, 3, 4, 5, 6 letters or 6 switches. We can do better than that. This set of double parentheses right here, this requires us to factor out, but this is the non-traditional kind of distributing, the kind of distributing that doesn't work in traditional algebra. Notice that there's an A in both. You can pull that out. But the A was added on to B, and it was added on to C, which means when you pull it out, it's going to be added on to what's left. And what's left is a B and a C, and since those were multiplied, that's just B times C. So the A factors out to leave us with A plus B times C. Now the BC that was here will stay, but you can kind of see what's going on here. We don't really need those parentheses, so we could call this A plus BC plus BC. But the idempotent property says that if you're going to have a banana with some cherries or a banana with some cherries, that's really just redundant. We can say that that is just a banana with some cherries. So we have A plus BC, and that is simplified. We got that down to 3 switches instead of 2. If that makes sense, great. If not, go back and watch that again, but that ability to factor out of 2 parentheses like this when you have a common term, that's tricky business. And I want to make sure you understand that. Okay, here's the last problem of the day, but this is a bit of a doozy. Kind of a fun one, actually. I would like you to see if you can simplify this Boolean expression. There's a lot going on, but boy, does it simplify. Pause the video, see what you can do here, get that thing simplified, and unpause to see if you end up at the same spot as me. Let's start by taking care of some of the simpler things that pop out at us here. Let's start with this negation of A. We can distribute that in. When we do that, we get the negation of A times A plus the negation of A times B. That's pretty straightforward. Now, we've got added to that B plus A times A, but that's the idempotent property. We can just say that that is B plus A. If you had some apples and some apples, that really just means you had some apples. Times A plus the negation of B. Okay, well, let's go a little bit further here. The negation of A and A, that will be a 0. That can never be true. If we have A and its opposite in series, then no current is going to flow. That's really 0. Or the negation of A times B, we can't do anything with that. Now, here's a case just like the one I showed you in the last example. We have a common factor of A here. We can undistribute that. We can pull that out and we get A. But A was added to both, so we're going to have A plus. And what's left behind here is a B and the negation of B. And those two are multiplied together. And so this part of the expression right here becomes that. A comes out, it's added to the product of the two that are left. Okay, well, the 0 doesn't need to go any further, so we have the negation of A times B, or A, or B and its negation. That's the same thing we saw up here. The negation of A times A is 0, and the negation of B times B is also 0. So that means that this simplifies to the negation of A times B or A. Now that feels pretty good. We're almost there, but we can actually go a little bit further, and here's why. I'm going to switch the order of these two and write A plus the negation of A times B. That's really the commutative property that lets us do that, although that's a pretty intuitive property. Now we can use that unusual kind of distributing that doesn't work in regular algebra. We can distribute in this A, and what we end up with is A or the negation of A times A or B. That is to say, we're distributing in the A over each of these, but the operation becomes addition, and those two parentheses are multiplied together. The reason that's useful is because A or the negation of A, that's really just 1. And so we have 1 times A or B, but by the identity property, 1 times A or B is really just A or B, and now we're done. We got it down to 2 switches, which is a pretty dramatic simplification compared to a pretty messy network. If you got that, great job. If not, you might want to watch that process again. There's a lot of properties being put into play there. Okay, well, I'll be the first to say that those Boolean algebra properties are tricky. The good news is that there's another way that you can simplify networks as well that is particularly clever. So practice your simplification in this assignment. Make sure to let me know if you need any help or visit the Math Center. And in our next lesson, we're going to look at another very clever way to take an expression, kind of like the ones we did today, and simplify them without the use of all those properties. So go ahead and we'll see you in the next lesson.